Okay, we're now going to do an example in which um, we derive a joint distribution involving, we do a change of variables involving gamma random variables. So let's think about so what we're going to do is we're going to say that x1 is gamma alpha lambda, x2 is gamma beta lambda, and they're going to be independent. So notice that they have the same intensity, lambda, but different shape parameters. Okay. And we're going to define S as the sum of x1 and x2. And we're going to define R as the relative size of x1 to the sum. So one thing to note is that S is non-negative and R is between 0 and 1. And so essentially what this looks like is if we have x1 and x2 and we stack them on top of each other, well, so x1 is here, x2 is here, then S is here, and R times S is here. Right, R times S is x1 product of R and S. So that's what these variables are. So S, so we need to invert this transformation. So S is x1, R is x1 over x1 plus x2. We've already shown, so x1 is equal to R times S. X2 we can show is equal to 1 minus R times S, because 1 minus R is x2 over x1 plus x2. Okay, well, what's the density of x1? Right, so the density of x1, right, is lambda to the alpha x1 to the alpha minus 1 e e to the minus lambda x1 over gamma of alpha, right? So then, and similarly for x2, lambda to the alpha, lambda to the beta, x2 to the beta minus 1, e to the minus lambda x2 divided by gamma of beta. Okay. Okay, so now we have the joint density of x1 and x2 by our assumption of independence is the product of lambda to the alpha, lambda to the beta. Just going to group these together, gamma alpha, gamma beta, x1 to the alpha minus 1, x2 to the beta minus 1, e to the minus lambda x1 plus x2. And this is for x1 and x2 having to be non-negative. Okay. So then from this, we derive f of SR has to be f of x1, x2, evaluated at the quantities x1, x2 in terms of S and R, right? So it's RS 1 minus RS plugged in times the determinant. And it's the determinant of dx1 dr, dx1 ds, which is R, dx1 dr, which is S, dx2 ds, which is 1 minus R, dx2 dr, which is minus S. And that determinant, see what that determinant is shortly. So how does all this shake out? So how this shakes out is we have lambda alpha, lambda beta, gamma alpha, gamma beta, RS to the alpha minus 1, 1 minus RS to the beta minus 1, e to the minus lambda, x1 plus x2. x1 plus x2 is S. And then here what we have is we have, in this determinant, we have minus RS minus 1 minus RS. This value is just S. So what we're left with is lambda alpha, lambda beta. Hey, gamma alpha, gamma beta. What can we say about this? Well, we can say that this is equal to, so R to the alpha minus 1, 1 minus R to the beta minus 1. Then we have S to the alpha plus beta minus 2 times S over here, this additional S here. So we can add another S, e to the minus lambda S. And I left out the indicator, so I have to be careful here. 0 to infinity x1, which is RS. 0 to infinity x2, which is 1 minus R. S. So the only way for that to be true is this is going to require R to be between 0 and 1, as we already know. And it allows S to be unconstrained. Okay. And okay, so what can we do next? Well, one thing that we can do is what we see here is we have S to the alpha plus beta minus 1. So let's see, we have, let's put it this way. Okay. Gamma alpha, gamma beta, R to the alpha minus 1, 1 minus R to the beta minus 1. Indicator. Zero to 1 of R times lambda to the alpha plus beta, S to the alpha plus beta minus 1, e to the minus lambda S, indicator for S from 0 to infinity. And so we do have a product. One is in terms of S, one is in terms of R. And what's missing here is this looks like the density of a gamma right, with intensity alpha plus beta, well, no, with shape parameter alpha plus beta and intensity lambda, except it's missing the denominator of the gamma function evaluated at A plus B. So alpha plus beta. So if we put that in, we have to get rid of it. So let's put it up here. Okay. So we already should know, or should have expected that S would be a gamma because it's the sum of independent gammas. Sum of independent gammas is a gamma, which we've derived before. And now here what we see is indeed that is the case, and S is independent of R. And R is what has what's called the beta distribution. So this is beta, alpha, beta. And so this is, and R is independent of S. We prove that R is independent of S by deriving the joint density of R and S and showing that it's a product. Okay, so this gives us our definition of the beta distribution. Suppose that we have parameters alpha, let's do this, alpha and beta positive, then a random variable X with a density given by gamma function, ratio of gamma functions, x to the alpha minus 1, 1 minus x to the beta minus 1, requiring x to be between 0 and 1, has the beta distribution. With parameter alpha, beta. Okay, so we derived the beta distribution. We're gonna come back and talk about some other properties of the beta distribution. But we derived it here as the relative size of one independent gamma random variable to the sum. That's how we derived it in this exam. So turns out the beta distribution does have some connections to other distributions we've dealt with in other cases. And so we'll come back, we'll talk about that in the next video.